Hey guys, how are you all? I hope you all doing well. Okay, today we are going to start the preparation of aldehyde and ketone. Okay, so first we start with hydration of alkyne. Okay, look here. This is the CH double bond CH react with H2SO4. Okay, at the time it gives rise to CH2 double bond CH HSO4. Okay, HSO4. Again it react with water. At the time there is a formation of vinyl alcohol. It undergo the keto-enol tautomerism. Your product is your aldehyde. Okay, if I am taking only the ethane, then only I am able to get this aldehyde. Okay, so from the alkyne, the only one molecule we can convert it into aldehyde, okay, by this reaction, that is ethane. Okay, but if I am taking the propine, if I am taking the butane, at the time I am able to get the only ketone, not able to get the any aldehyde. Okay, so only ethane in this reaction lead the aldehyde. Rest of the whatever the alkyne you are taking in this reaction, you are going to get only ketone. Okay, next we are going to discuss the preparation of aldehyde. The first one is your benzyl chloride. Okay, this is benzyl. Okay, so this is chloride, so this is benzyl chloride. When it undergo the Rosamond reduction, if I am not using the BaSO4, okay, if I am using only your hydrogen and palladium, at that time I am able to get the alcohol. Okay, so in order to restrict the reduction reaction in between, I have to use the barium sulfate as a catalytic poisonous. Okay, so the next, the nitrile are reduced to corresponding imine. Okay, look here, this is your nitrile. The nitrile reduced to corresponding imines. Okay, so this get hydrolyzed. Okay, then only you are able to get your aldehyde. Okay, so if I want me to explain this, I will explain. Look here, NH, if there is a bond formation, okay, then what it going to lead? It is going to lead OH and NH2. Okay, so then the H plus, this is lone pair of electron, right? Here the lone pair of electron is there, it is coming here. So this lone pair of electron accepts the proton, then you will get your aldehyde. Clear? Right. So next we are taking the nitrile are selectively reduced by diisobutyl aluminum hydride. What is diisobutyl aluminum hydride? So aluminum bonded with hydride, so diisobutyl, right? So this is CH, then this is your isobutyl, this is how many times? This is diisobutyl, right? So 2 times diisobutyl aluminum hydride, this is dipole. Okay, so this reagent will convert the your cyanide, okay, your nitrile or cyanide, and your ester converted into aldehyde. Okay, look here, so this is your cyanide which is converted into aldehyde. Okay, so in this reaction also, the first step, when we using the cyanide, your first step going to be your imine only. Okay, this can be further hydrolyzed, then only you are able to get your aldehyde. Okay, so your cyanide become aldehyde, again your ester converted into aldehyde. Clear? Then from hydrocarbon, so aromatic aldehyde, benzaldehyde and its derivative are prepared from the aromatic hydrocarbon by the following method. So when I am using the toluene, so this toluene in presence of strong oxidizing agent, it will be converted into benzoic acid. Okay, so but here the case is not very strong oxidizing agent, we are using the mild oxidizing agent. So strong oxidizing agent oxidize the toluene and its derivative to benzoic acid. Okay, so however it is possible to stop the oxidation at the aldehyde stage. Suitable reagent that convert the methyl group of intermediate, it is difficult to oxidize further. The following methods are used for this purpose. So first one is your chromyl chloride and oxidize the methyl group into chromium complex. Okay, then which on hydrolysis give the corresponding benzene. Your reaction is here. Look here. This is your toluene. So toluene react with chromyl chloride in presence of your non-polar solvent carbon disulfide. So this complex is like here. So look here, this is your complex. So CH. Then so this will be bit bigger molecule. So I will write it here. So this is your benzene. So this connected with CH, then O or C, then double bond O, then OH, then Cl. Okay, so this side also O, Cr, double bond O, OH and Cl. This is your chromium complex. Okay, this on hydrolysis, if I am adding the H2O, so O will come here, hydrogen will come here, hydrogen will come here. This is the breakage. Like this happen, then only there is a formation of your benzaldehyde. Then only your formation of benzaldehyde. Clear? Right. So here, this is the Etard reaction when we use the chromyl chloride. The use of chromic oxide, the toluene or substituted toluene. So toluene, like this is your toluene. Okay, substituted toluene means like here CH3, here the chlorine is there. So this is substituted toluene. Okay, so toluene, substituted toluene is converted into benzaldehyde diacetate, treating with chromic oxide, acetic anhydride. So benzaldehyde diacetate can be hydrolyzed, corresponding benzaldehyde in aqueous acid. Perfect. Look here. So this is your chromic oxide, this is your acetic anhydride. When it react with 273 to 283 Kelvin, at the time your chromium complex will be formed, right? This is your anhydride complex. So O, C double bond O, CH3. Here also O, C double bond O, CH3 is there. This when it react with water, this side hydrogen, here hydrogen, here hydrogen. Okay, so this become a CHO, this become a CHO. So your product is benzaldehyde. Clear? Right. Next reaction, when toluene react with chlorine. Okay, so you know that, right? This is free radical mechanism. Your toluene carbon. Okay, this is, so it undergo the substitution reaction in presence of chlorine and sunlight. Okay, at the time first one hydrogen get replaced, after that two hydrogen get replaced by chlorine, so we will get the benzal chloride. Okay, this benzal chloride in presence of water, what it become, this became a benzal diol. Okay, so this is the, so when we heat at 373 Kelvin, so this OH, this hydrogen can be converted into H2O. Okay, what is remaining? CHO is remaining. So your benzaldehyde. Clear? Then your Getterman-Koch reaction. Getterman-Koch reaction. So when benzene and its derivative, is treated with carbon monoxide and hydrogen chloride in presence of anhydrous aluminum chloride, and cuprous chloride, it gives rise to benzaldehyde or substituted benzaldehyde. So your benzene is there, in the all the position hydrogen is there. This hydrogen, when it combined with carbon monoxide, it going to form a CHO in presence of HCl. So this is the reaction condition. This is used as a catalyst. Okay, so this reaction is, we call it as a Getterman-Koch reaction. Then one more reaction I want to explain in a very great detail. So look here. So 2RMgX. Okay, so this is Grignard reagent. So this is going to be your positive, this is going to be your negative. Then if I am taking the cadmium, so this is 2 plus and the Cl minus is there, Cl minus is there. So this is the, here is there is a cleavage and here is the cleavage. Okay, so this two alkyl group going to join with cadmium, at the time it going to formation of the dialkyl cadmium first. Okay, then this Cl, this 2Cl combine with this MgCl. Okay, so at the time MgCl and X, this is the your product. Okay, so next your acyl halide. We know that, right? This is Cl minus and this is a plus. Okay, so 2 times of I am taking. So again CD, cadmium is there. The cadmium is positive in nature. The R is minus in nature. This R minus going to attack this positive. So at the time R, C double bond O, R will be formed. Okay, so 2 times of, if I am take this R dash in the this acyl halide. So at the time R dash C double bond O R. Okay, so your finally we will get the cadmium chloride back. Okay, clear? Cyanide, from the cyanide we are making the ketone by using the Grignard reagent. Okay, so look here. So we know that, right, this C6H5 going to be minus, this is going to be plus, this minus going to attack the carbon. Okay, at the time this pi bond move to the nitrogen. Okay, so this nitrogen abstract the MgBr. Okay, so what it going to form? This is the product it's going to form. If I'm using the water at the time, oxygen, this is hydrogen. Okay, so what is the your byproduct? MgNH2. Okay, and Br. Okay, clear? Right. So next we go for the benzene or substituted benzene. Okay, the benzene, your substituted benzene, whatever it might be, if that substituted benzene undergo the Friedel-Crafts acylation, we can use it. Say for example, if I am using the chlorobenzene, okay, the chlorobenzene which is undergo the acylation, at the time it give rise to ortho and para product, right? This is your ortho product. Then one more product is your para product. Okay, so this is your ketone only. Okay, ketone only. This reaction we discussed in where? We discussed in the first lesson itself. Okay, so by using the acyl chloride and anhydrous aluminum chloride. Anhydrous aluminum chloride. So this is the example for the substituted your benzene. Okay, so substituted benzene also which undergo the reaction and the formation of your ketone. Okay, so first here, look here, this is RCl, right? This is plus, this is minus. We know that, right? This is hydrogen, this is plus, this is minus. So this plus going to, this minus going to attack this plus, or this minus going to attack the hydrogen. Okay, so your byproduct is HCl. Right. Next, what is the reagent we are using in order to form the product? Okay, the first product is, so look here, xenol, alcohol converted into Al means aldehyde. So alcohol converted into aldehyde, we have to use the oxidizing agent. Okay, so that is pyridinium chlorochromate. Next one is again cyclohexanol become a cyclohexanone. So here alcohol to your ketone. Okay, your alcohol to ketone. What is the reagent we have to use? Is anhydrous CrO3, that is chromic oxide. Next, this is substituted toluene, right? So parafluorotoluene to parafluorobenzaldehyde. So toluene to benzaldehyde, what is the reagent we have used? We used, okay, two reagent. One is Etard reaction, another one is acetic anhydride. Okay, so CrO3 in presence of acetic anhydride, or we can use the chromial chloride and water. Okay, so next fourth one, ethane nitrile to ethanol. Okay, ethane nitrile to ethanol. So obviously this is we can use the HCl and the tin chloride, right? So instead we can use the diisobutyl aluminum hydride also, because diisobutyl aluminum hydride which convert the your cyanide and your ester into aldehyde. Okay, so next allyl alcohol to propanol. Okay, pyridinium chlorochromate we can use again. So in case of but2ene to ethanol, so this is your but2ene, CH3 CH double bond CH CH2. This is but2ene, right? If it undergo the ozonolysis in presence of O3 and H2O, zinc dust, at the time the breaking will happen. This side one oxygen, this side one oxygen. At the time there is a formation of 2CHO. Okay, so there is a intermediate formation in a different way that is not needed. Okay, nobody ask. Okay, they will ask the reactant and give the your reagent, what is the product they will ask. Okay, so this is not much important. So just to break this reaction is more important, but we need not to go in a systematic way. Just to break the double bond, both side add one oxygen. Okay, we'll get the aldehyde and ketone in the ozonolysis. Clear? So shall we go for next? Look here. So this is your benzene. Okay, this is your ethanol. Okay, so propanyl chloride give rise to, what is the product? The first product is this one. Number one, it is undergo the acylation in presence of AlCl3. This is your product. Okay, so 1 2 3. Okay, next this is your cadmium chloride, right? So benzyl, right? C6H5 CH2 C6H5 CH2, this is cadmium, right? Okay, so this is 2CH3 C double bond O Cl, clear? So this is your minus, this is your minus, this is your 2 plus, then this is plus, this is minus. Okay, attach the plus and minus. Okay, so you will get the CH3 CH2 C double bond O CH2 and pH is C6H5, clear? So this is your product. Okay, your byproduct is cadmium chloride, clear? Right, this is your second reaction. Okay, so when it comes to third reaction, what is there? So I already told you, if I am taking the ethane in presence of HgH2SO4, that time I will get the your aldehyde, but in case if I am taking the propane or butane, at the time I am able to get the ketone, right? So CH C triple bond CH. Okay, if I am using the H2SO4, what I am able to get is, this is H plus HSO4 minus, so CH3 CHSO4 double bond CH2. Okay, when it undergo the hydrolysis, okay, CH3 COH and double bond, this is enol form, right? So this enol form converted into keto form, so this is, we call it as a tautomerism. Okay, what is happen is, here there is a double bond is, sorry, here there is a lone pair of electron is there, right? So this lone pair of electron come here, this pi bond come to here, this become a negative, this negative abstract the proton, at the time there is a formation of ketone. Okay, clear? The third reaction. Then when it come to fourth reaction, that is very easy one. Okay, we are using the chloride, so this is substituted toluene, so this can be converted into CHU, this can be converted into CHU. Am I right? Clear? So look here, this is physical property, right? Okay, so physical properties of aldehyde and ketone described follow. The methanol is a gas at room temperature, ethanol is volatile liquid, other aldehyde ketones are liquid or solid, okay, at room temperature. The boiling point of aldehyde and ketones are higher than those of hydrocarbon, ether, comparable molecular mass. It is due to weak molecular association, aldehyde and ketone arising out of dipole-dipole interaction. Also their boiling points are lower than those of the alcohol. The molecular mass, similar molecular mass due to absence of intermolecular hydrogen bonding. So if I compare the boiling point of your aldehyde and ketone with your ether and hydrocarbon, at the time your aldehyde ketone is more boiling point, because there is a dipole-dipole interaction present in your aldehyde. Okay, so in case if I am compare your aldehyde and ketone with alcohol, this going to be less boiling point compared to your alcohol, because of in alcohol there is a presence of intermolecular hydrogen bonding. Clear? Right. So I will explain the detailed way by solving the next question in the example sums. Okay. So next, there is a lower members of aldehyde such as methanol and ethanol and propanone. Okay, ethanol and propanone are miscible with water. Okay, miscible with water. So methanol, ethanol, propanone is miscible with water. Miscible with water is important. Okay, in all proportion, because they form the hydrogen bond. That is very important. Okay, so aldehyde ketone, lower member of aldehyde ketone, that is methanol, ethanol and propanone, which is mixed with water, because of it is able to make the hydrogen bond. However, the solubility of aldehyde and ketone decreases. So say for example, if I am taking the methanol, then I am taking the ethanol, okay, I am taking the propanol, I am taking the butanol, I am taking the pentanol. So your carbon chain get increases, right? So this carbon chain is repulsive in nature. Okay, that is hydrophobic in nature. It repel with water. Okay, so at the time the chain get increases, your solubility get decreases. Okay, so aldehyde and ketones are fairly soluble in organic solvent, benzene, ether, methanol. chloroform. Okay, so lower aldehyde, leave the sharp pungent. Okay, if this is lower number of carbon, right? So in the aldehyde ketone, this is the lower member. So this is pungent in smell. Okay, it is not a sweet smell, pungent smell. Your carbon number get increases at the time pungent smell get decreases. Okay, if it carbon number increases, carbon chain increases, your pungent smell get decreases, your fragrant smell get increases. That is more important. Okay, clear? So next we go for the question number 12.2. Okay, so they given the your butanol which is given. Okay, then your butanol is given, then diethyl ether is given, ethoxyethane is given, your butane is given. So we know that, right, your alcohol going to be highest. Okay, your alcohol going to be highest in boiling point because it is able to make the intermolecular hydrogen bonding. So but in case of next two thing, okay, so one is ether, another one is aldehyde. Both are making the dipole interaction. But if you take your aldehyde, the dipole interaction is much more or much stronger in compared to the ether. So this two having the dipole interaction, but in case of your butane, it is not having the dipole interaction. It has only one interaction, only one force of interaction, that is van der Waals force. Clear? Go for the next. So here there is a chemical properties of aldehyde ketone we will discuss. Before that we will discuss some questions. Okay, so in this also there is a alcohol is there. This is going to be your more boiling point. Okay, so increasing order, right? So your alkane is going to be lesser. Okay, so this is your next one. Then aldehyde and ether, so aldehyde will be more compared to your ether. Clear? Right. Next we go for the nucleophilic addition. Okay, nucleophilic addition. So what is nucleophilic addition? The addition reaction initiated by your nucleophile. What is nucleophile? I explained in a great detail in the first lesson itself. Alloalkane, alloarenes. Do watch that video and get to know what is nucleophile exactly. Okay, so if you know that, just comment it. Clear? So the mechanism of nucleophilic substitution reaction. So your nucleophile attack your deficit carbon. At the time this pi bond move over the oxygen. At the time this oxygen abstract the proton, there is a formation of OH. Clear? So your nucleophile attack the electrophilic carbon. Okay, because the carbon is electron deficit one, your nucleophile is electron rich one. Okay, so approximately perpendicular to the plane sp2 hybridized orbital of carbonyl carbon, the hybridization of the carbon change from sp2 to sp3, because in ketone there is a presence of 3 sigma 1 pi, but in case of the nucleophile attack, after that we will get the 4 sigma bond, so it become a sp3 hybridized one, right? So and tetrahedral alkoxide intermediate is produced. So this is the tetrahedral alkoxide. So this intermediate capture the proton medium to give the electrically neutral product, the net result of addition of nucleophile and H plus across the carbon double bond as shown in here. So when it comes to the reactivity of aldehyde and ketone, so if I am taking the aldehyde and ketone, so one side there is a carbon, in another side there is a hydrogen, right? But in case if I am taking the ketone, both sides there is a carbon is there, right? So in this side only one bulkier group in case of your aldehyde, but in case of if you are taking the ketone, at the time both side there is a bulkier group, right? At the time the nucleophile not able to attack, okay, easily because of steric hindrance, okay, that is there in the reactivity. When it comes to would you expect the benzaldehyde is more reactive or less reactive nucleophilic addition reaction compared to the propanol? So if I am taking the propanol, look here, this is your propanol. Okay, this is your propanol. Then one more example, what they given the benzaldehyde. Okay, so if I take this, so this is electron releasing group. Okay, so this is neutral in nature. Either it will not either it release the electron, or it neither release nor pull the electron. Okay, so at the time, so this get more polarized. Okay, this become minus, this become a plus. But in case here the oxygen also pull the electron towards itself, then benzene ring also pull the electron towards itself. So this is minus A effect. Okay, So at the time here there is a more polarity on carbon and oxygen, but here in case the carbon oxygen not that much polarity compared with your propanol. So that is the reason why your propanol is more reactive. Okay, so I will stop here. Thank you all. Any doubt, okay, in this video, just comment in a comment box. Okay, I will answer.